Hello students, welcome to 15th lecture of chemical bonding and molecular structure. In previous lecture we discussed about hybridization involving s, p and even d orbitals. And we also discussed about the shape and type of bonds. And we also discussed that if elements have empty d orbital, then as per their requirement they can use it in hybridization, and that's why d orbital is also part of hybridization in some cases. Now let us discuss one more theory which can explain some of the molecular structures. Now keep in mind, not all of them are perfect. In earlier times we do not have much data or knowledge about the molecules, so that's why we need some theories which can explain molecular formations and their behaviors. That's why in different eras different scientists developed different theories. And those theories were not perfect, and that's why we need some other theories which can explain which previous theories was unable to explain. So that's why we have these multiple different theories which explains molecular structures, and they address different portions, and all of them are sometimes they are closer to each other, or sometimes they use same principle, and sometimes they use completely different principles. So now let us talk about molecular orbital theory. So molecular orbital theory was developed by F. Hund and R. S. Mulliken in 1932. The salient feature of these theories are, as mentioned below, the first, electron in a molecule are present in a various molecular orbital as the electrons of atoms are present in various atomic orbitals. So that means we have to arrange electrons in molecule just like we arrange them in atoms. The atomic orbitals of comparable energies and proper symmetry combine to form molecular orbitals. That means keep in mind they are same orbitals. Orbitals present in atoms are now molecular orbitals when they form molecule. Third point, while the electron in atomic orbital is influenced by one nucleus, in a molecular orbital it is influenced by two or more nucleus depending upon the number of atoms in the molecule. That means in atom we only have one nucleus, that's why electron feels attraction or repulsion towards the single nucleus only. But in molecule we have more than one atom, sometimes 2, 3, 4, 5 and so on. As we discussed in previous point, SF6 molecule contains total 7 elements or 7 atoms in it. So same thing is applicable in this theory. When we have multiple atoms combined with each other in a molecule, they all will affect electrons present in them. And thus atomic orbital is monocentric while the molecular orbitals are polycentric. Mono that means single and poly that means multiple. The number of molecular orbitals formed is equal to the number of combining atomic orbitals. That means if you have 5 orbitals in atom, then you will get 5 orbitals in molecule, no less, no more. When two atomic orbitals combine, two molecular orbitals are formed. One is known as bonding molecular orbital while the other is called anti-bonding molecular orbital. And as the name suggests, bonding molecular orbital will support the bonding while anti-bonding molecular orbitals will oppose the bonding, and we will discuss it in the structural discussion. Fifth point, the bonding molecular orbital has lower energy, hence the greater stability than the corresponding antibody molecular orbital. Just as the electron probability distribution around the nucleus is an atom is given by the atomic orbital, the electron probability distribution around a group of nuclei in a molecule is given by molecular orbital. So that means it is a definition of orbital. There is no rigid shapes present around the atoms. It is just a possibility which we called orbitals. Okay, possibility or probability of finding electron in certain region is called orbital. So if we are trying to find electrons around the atom, then it is atomic orbital, and if you are trying to find electron around the molecules, then it is called molecular orbital. Next point, the molecular orbital like atomic orbitals are filled in accordance with the Aufbau principle, obeying the Pauli's exclusion principle and Hund's rule. So all of these rules were already discussed, so same rule will be applicable in this case as well. If lower energy orbitals are empty, then electron won't jump into higher energy orbital. Okay, electron only goes into higher energy orbitals when lower energy orbitals are fully filled. And if similar energy orbitals are present, then pairing won't start. Until all of the equal energy containing orbitals are half filled, then pairing will start. and same spin containing electrons cannot be paired in an orbital. Okay, so these three rules are also applied in molecular orbitals. So next point, how can we form the molecular orbitals? And here is how formation of molecular orbitals, linear combination of atomic orbitals. According to wave mechanics, the atomic orbitals can be expressed by wave function Schrei, which represents the amplitude of the electron waves. Okay, so here we are talking about the duality nature. We know that each and every particles and waves, both of them have both type of nature. That means particle nature as well as wave nature. As the size increases or mass increases, wave nature decreases and particle nature increases. That's why our daily life objects almost acts as a particle, and you cannot observe their wave natures easily, but they are wave natures as well. Okay, they have duality. So this whole theory is mainly based on wave nature of particles, and in this case wave function will be expressed for atomic orbitals, and these are obtained from the solution of Schrodinger's wave equation. However, since it cannot solve for any system containing more than one electron, molecular orbitals which are one electron wave functions for molecules are difficult to obtain directly from the solution of Schrodinger's wave equation. Now Schrodinger's wave equation is not in our syllabus. Okay, so we are not going to discuss it in detail, and it is also very complicated. And other thing is, it is imaginary. No such actual wave functions are present inside the molecule. So it is earlier times theory and it has some limitations. So it is not accurate and it is not completely based on true data. It is based on imaginations. But still these imaginations can explain some of the phenomena or some of the points in bond formation. So we are going to discuss it. And each false or older theories are actual base of new and accurate theories. Okay, so this is one of the base of more accurate theories. So that's why we need to understand it. Now to overcome this problem, an approximate method known as linear combination of atomic orbital LCAO has been adopted. Let us apply this method to homonuclear diatomic hydrogen molecule. That means we are using simplest molecule to start with. Consider a hydrogen molecule consists of two atoms A and B. Both of them are hydrogen. First hydrogen atom is called A, second is called B. Each hydrogen atom in their ground state has one electron in one s orbital. We know that the atomic orbital of these atoms may be represented by the wave function Schrei A and Schrei B. This trident like symbol is called Schrei. Okay. Mathematically, the formation of molecular orbitals may be described by the linear combination of atomic orbital that can take place by addition and by subtraction of the wave function of individual atomic orbitals as shown below. That means simply assume that instead of representing them as a probability, we are talking about orbitals, we will represent them as a Schrei, and let us assume Schrei is a one value of a certain digit. Okay. We don't know about its value right now, but let us assume Schrei has some specific value, and you can just add or subtract these values from each other. So as mentioned earlier, we have two different hydrogen atoms A and B. For A, we will consider Schrei A as a wave function, and for B, Schrei B is its wave function. So when these two orbitals combines with each other, either by subtraction or by addition, they will produce molecular orbital. Okay, so simple subtraction or addition will give us molecular orbitals as shown below. So Schrei MO, MO represents molecular orbital is plus or minus Schrei A and Schrei B. Okay, that means either addition or subtraction. With addition and with subtraction, you will get different type of orbitals, molecular orbitals. Therefore, the two molecular orbitals sigma and sigma star are formed as sigma will be product of summation of both of them, and sigma star is a product of subtraction of Schrei A and Schrei B. Now what sigma and sigma star represents? So as we discussed earlier in salient feature of this theory, it was mentioned there are two different type of molecular orbital, bonding and anti-bonding. So normal sigma represents bonding orbital and sigma star represents anti-bonding orbital. And as we know, when two orbitals combines linearly, or if they are present on single axis, then they will overlap on each other straight. That means it will form sigma bond. So both of the orbital, let us assume this is the first orbital and we have second atom's orbital on same axis, and these type of overlapping results in sigma bond. Okay, so that's why we represented them as a sigma, and it is also mentioned in the name of the topic, linear combination of atomic orbitals. We are combining them in a straight line. So with addition, bonding molecular orbitals are formed, and with subtraction, anti-bonding molecular orbitals are formed, and we can represent it using these type of diagrams as well. So let us understand this simplest diagram of molecular orbital. Why simplest? Because we are talking about hydrogen molecule, which is simplest molecule of all of them. So now let us discuss this basic graph or representation of molecular orbitals. So we can divide this graph in three parts, these two parts. Okay, between these two lines we have molecular orbits, and on left and right hand side we have two different atomic orbitals. Okay, as we already discussed, we have two hydrogen atoms combining with each other to form H2 molecule. So on left and right hand side we have hydrogen atoms and their orbitals, and at the center we have H2 molecule. Okay, and keep in mind they are not separate. Okay, they are not separate entity. Each atoms of hydrogen will combine to form molecules. So just keep in mind, here one hydrogen and here is a second hydrogen, and both of them will combine to form H2 molecule present at the center. They are not separate one. Okay, that means in the center we have hydrogen molecule and we have another hydrogen atoms. No, that is not the case here, but hydrogens present on each side are actually combined to form H2 molecule at the center. So as the mentioned earlier, wave function of first hydrogen atom, which is called A, and wave function of second hydrogen atom, which is called B. When they combined, we have two atomic orbitals, atomic orbital of first hydrogen and second hydrogen. So we have two atomic orbitals, that means you will get two molecular orbitals. One of them will be bonding molecular orbital and one of them will be anti-bonding molecular orbital, which is already mentioned in salient feature. Now as mentioned in salient feature, bonding molecular orbitals will have lower energy than the anti-bonding molecular orbital. So as you can see here, increasing order of energy is mentioned. That means as you move from bottom to top, increasing energy order will be obtained. So when these two orbitals combine, two different molecular orbitals will be produced. So bottom molecular orbital, as the suggest, it is sigma, and it is addition of these two, Shri A and Shri B, and top orbital is sigma star, that means it will be anti-bonding, and which is subtraction of Shri A minus Shri B. So these two orbitals will be produced in case of molecule, and as we know, our both hydrogen contains one electron. So how many electrons we have? We have 2 electrons, and as we know, each orbital can occupy 2 electrons max. So just like the rules discussed for atoms, same rule will be applied in this case for the arrangement of electron. First add the electrons in lowest energy orbital. If lowest energy orbital is fully filled, then shift the electrons in upper energy orbital. So we have only 2 electrons and each orbital can occupy up to 2 electrons. So both of these 2 electrons will enter in bonding molecular orbital of H2 molecule. Okay, so as you can see here, 2 electrons are mentioned and anti-bonding orbital is empty because we do not have extra electrons to add in it. We will discuss some examples in which you will have more than 2 electrons, so that these points will be clear. But right now for the hydrogen, each atomic orbitals have 1 electrons and each atoms of hydrogen have 1 orbitals. So they will combine in molecular formation and you will get 2 orbitals, bonding and anti-bonding. So both of the electrons will enter in bonding orbital and anti-bonding orbital will be empty. Quantitatively, formation of molecular orbital can be understood in terms of the constructive and destructive interference of the electron waves for the combining atoms. In the formation of bonding and molecular orbitals, the two electron waves of the bonding atoms reinforce each other due to the constructive interference, while in the formation of antibonding molecular orbital, the electron waves cancels each other due to the destructive interference. Now, what these terms means? So, these terms means wave nature of electron. As we already learned, interference is a wave nature, and interference, that means when two different waves combines with each other. Sometimes they will support each other and sometimes they will oppose each other. So when two waves supports each other, it is called constructive interference, and when two orbitals opposes each other, it is called destructive interference. And what happened when constructive interference happens? Constructive interference strengthens the waves. Okay, that means they will increase the intensity of wave, and the destructive interference will decrease the intensity of wave. That means they will make them weaker. Now practically, if you want to understand, then assume it like this. Suppose this is a wave A, and here is a wave B of a same type. Okay, so as you can see, they will support each other because they have same type of structure, and resulting wave, if we add these together, resulting wave will have higher energy than previous two. So this is the example of constructive interference. And destructive, that means combination of these two types of wave. As you can see, they are actually opposite of each other. Okay, so that's why resulting wave will be weaker. Let us assume both of them contains equal amount of energy, then resulting wave will be 0. Okay, energy of resulting wave will be 0. This is called destructive interference. Practically, you can do the practical with light. You need a box, a dark environment, and just poke holes in the box close to each other, and let the light from the outside come through the box. And when the light enters inside the box, you will see patterns of light inside the box. So obvious conclusion will be, if suppose we have a box like this and we just poked two holes in it, suppose like this, one hole at here, one hole at here. So our normal conclusion will be, if you look inside the box from particular angle, or let us put a camera inside it. So our normal observation should be only two dots of light should be visible inside it. One, because the light is coming through the first hole, and second, because the light is coming through the second hole. So you should be able to see only two bright spots inside the dark box. But this is not true, because waves do not travel like this straight line. We know that when we light up the bulb, our bulb's light or tube light's light will spread in all the direction. That means waves are moving like this. Okay, they will, as they travel away from this source, they will spread out and weakens. That means strength will be decreased. So that means when light beams will pass through these holes, they will spread out like this, or light waves actually will spread out like this. Okay, and as they travel, their strength also decreases. Okay, so second waves also pass like this. Okay, so as we can see, they are come in contact with each other at certain points. Okay, so at certain points they will interfere constructively, and certain points they will interfere destructively. So when constructive interference occurs, you will notice a bright spot of light, and when destructive interference occurs, you will see no light at all. So you will see series of bright spots inside the box. Although we poked just two holes, you will see more than two spots inside the box like this. Certain regions are bright, then dull, then bright, and then dull. These type of observation will be done, and same practical can be done with waves in water. So we are talking about this type of phenomenon with the example of waves of sound. Okay, same thing can be obtained with electron, and same thing can be obtained with light as well. So as you can see, these two waves have same type of structure. That means when these two waves coming out of a speaker placed too close to each other, you will notice we have constructive interference. That means sound intensity in this region will be louder than individual speaker. Okay, if you are listening from this point, then you will listen comparatively less sound, and if you are listening from this point, then you will notice sound is louder. But when we mix these type of wave with this type of wave, that means these two speakers, second and third, then opposite nature are combining with each other. That's why destructive interference will be produced. And if you listen from this point, almost no sound will be. So this is literally example of active noise cancellation. High quality handsets or earphones do use this technology to cancel out the sound coming from closer environment. Okay, our mobile phones regularly do these type of noise cancellation as well. So this is the example of constructive and destructive interference, and here is an example of interference of light. As you can see, first practical with single slit gives only one type of light. That means we poked a single hole on the top of the box, and you will see this type of result inside the box, only one spot. But when we put two holes close to each other on the top of the box, that means double slit, then you will notice multiple lines of dot, as you can see in this case. Okay, so each bright spot represents constructive interference, and each less bright or no light spot or empty spot between two bright spot is destructive interference. Okay, so this is actual image of light beams coming through these two holes. If you poke holes in the box close to each other, then this type of result will be observed inside the box. Okay, but you have to be careful, no light source other than two holes present on top of the box should be there, and proper light should be coming through that holes. Okay, so you can put your box in the open atmosphere, and then you can put camera inside the box, and you will notice this type of pattern. So bonding orbitals are considered as constructive interference, and anti-bonding are considered as destructive interference. And as a result, electron density in the bonding orbitals is located between the nuclei of the bonded atoms, and because of which the repulsion between the nuclei is very less, while in case of anti-bonding molecular orbital, most of the electron density is located away from the space between two nuclei. In fact, there is a nodal plane on which the electron density is zero. Okay, we already discussed about nodal planes, what it is, between the nuclei, and hence the repulsion between the nuclei is high. Okay, that means if we are placing two similar charges close to each other, then we know that because of similar charge they will repel each other, and repulsion, that means lesser stability. So if electrons are present between the two nucleus, that means they are not repelling each other because of presence of electron, and they will be stabilized. And when they do not have electrons between them, they will repel each other. Both nucleus of different atoms will repel each other, and that's why because of repulsion stability decreases. Okay, so this is the reason why atomic orbitals, bonding molecular orbitals, will increase the strength of bond, and anti-bonding orbitals will decrease the strength of bond. Electrons placed in bonding molecular orbital tend to hold the nuclei together and stabilize a molecule. Therefore, bonding molecular orbitals always possesses lower energy than the either of atomic orbitals that have combined to form it. In contrast, the electron placed in anti-bonding molecular orbitals destabilize the molecule. In this is because of mutual repulsion of the electrons in this orbital is more than the attraction between the electrons and the nuclei, which causes net increase in energy. And energy orbital order are visible from this graph as well. As we can see, energy of atomic orbitals are placed between the energy of anti-bonding and bonding orbital. So bonding orbitals have lower energy than atomic orbitals, and anti-bonding orbitals have higher energy than atomic orbitals. So that means energy, and as we know, according to thermodynamics rule, we cannot destroy or create energies, but we can convert them into one form to other form. So total energy will be same. Suppose the energy of each atomic orbital is 5 points. Okay, Suppose energy of this other orbital is also 5 point. So total energy in atomic orbital is 5 plus 5, 10. So it must be true for this molecular orbital. Now let us assume energy of bonding orbital is 2. That means when atomic orbitals combines, they forms bonding and antibonding orbitals. So energy of a bonding orbital decreases with 3 points and now it is 2. So energy of antibonding orbital will increase with 3 point and now energy of antibonding orbital is 8. So total energy 2 plus 8, again 10. Okay, so total energy of atoms is equal to total energy of molecule. But higher energy orbital is empty. That means no value of that higher energy orbital is being considered now. That's why electrons are stabilized and molecule is stabilized. It may be noted that the energy of antibonding orbital is raised above the energy of parent orbitals, and that have combined, and energy of bonding orbital has been lowered than the parent's orbital, that means atomic orbital. The total energy of two molecular orbitals, however, remains the same as the two original atoms, atomic orbitals. So as we discussed the point, same is mentioned here. So if you find any difficulty till this point, feel free to ask. In next lecture, we are going to move towards the complicated molecules which have more than 2 electrons, so that we can understand our points. Okay, so if you find any difficulty in case of hydrogen, feel free to ask so that you can understand the later topics. Thank you.